have coffee can work. So we're going to do DPLL, CDCL. This is the I believe it's Davis-Putnam algorithm. The Davis-Putnam Logeman-Loveland algorithm, DPLL. And then we're going to do CDCL, the constraint, man, I can remember, conflict-driven clause learning algorithm. And so where I'm at is Wikipedia, actually. I haven't actually programmed these algorithms, but they're in a lot of SAT solver frameworks. So we start with Davis-Putnam, and I'm sharing the wrong window here. So I'm going to share my Python window, because we're going to start with Python before we go to C here. So let me fix that, because that is a problem. So we're going to change the share window away from Visual Studio. I did get the cross-compiling done with, cross-compiling. I did get the assembly language portable, so it compiles on Linux, and with 32 and 64-bit. And I did manage to get the code, the C++ code now compatible Linux and Windows. So, but it doesn't work there. It's segment faulting and other stuff. I was using REPL.it to test it, but I need to go more into detail, but I've decided to do something fresh for the current moment. Sounds more fun. Uh-oh. Uh-oh. Oh, there it is. Okay, there we go. So, yeah, I got a lot of stuff going on over here in Python. Let's just take a look at this. It's the same stuff, the virtual machine model, the first thing we're going to do here is we're going to do this methodically. So this isn't going to be like necessarily a fast job, but we can go to this SATlib website. SATlib has benchmark problems. Now, we do not want complicated instances. Now, SATlib's benchmarking problems can be with all sorts of different things, but they've got 3SAT. Well, 3SAT is a SAT problem. We don't, in the algorithms I'm talking about are SAT. They're not special for 3SAT. There are some special for 3SAT algorithms, but we're not going to do those at the time being. They still are exponential, but they've got like ways of, 1.2 to the power of k type of exponential. So the key is to go to the SATlib. So what I'm going to do is I'm not going to download it. I'm going to say, hey, I found on SATlib the link. That's the link. But then I found this link. So, well, download it. Why not? Can't Python do such a thing? So I search for downloading a file in Python. In fact, I don't know how to do this off the top of my head, but Python 3, look at this. Import earllib.request. Let's do it. For now, we're going to, of course we need to do something better, but we can just say, get satlib or something. So first, look, we import earllib.request. And then we can say urlib.request.open.read.decode or something like this. I don't know if any of this works, but... Ooh, but we've got a tar gz, so... We don't even need a comment here. We can just, for now, just make a string. So there we go. So the problem is I want to download a gzip. Now I see another example. If the zip is big enough, we probably have to use buffering and these types of things, but... Wow. So I'm going to search for downloading a tar gz and see what people have come up with. But the question is actually how to unzip it. Requests.get. I don't know what's best here. I see there's also this one. Because we're doing a binary file. This looks a little more low level than the urllib, but we'll see how this works. Of course, I don't want to get too hung up on this, but... Now, I don't actually want to write this to the disk. I actually want to just extract a gzip file. So we do response.raw.read. Of course, I don't want to hammer their servers, but maybe we should save the file just for, for being graceful here. Yeah, I think that's the right way to do it, at least. You can always change it later, but to not hammer the server is always a better idea. Now, we probably could parse that off, but I think with open for WB as out file, then we can oh, we're supposed to check this to be a 200 OK response. Because now what we can do is, while we're trying to figure out how to do this, we can see if a file exists. Again, this is just being elegant to set up a nice testing framework, totally kind of self-contained here. So this is random 3sat, but it won't be a huge instance, but it'll be big enough that it'll be challenging to solve. So if it already exists, we can also extract it. Now, I don't know how to extract a tar gz. if there's like a nice library to do that. I'm getting my coffee. Need coffee for this type of project. This is why taking so long to order the machine. Forcing it. Forcing the issue with the coffee. There's no doubt we're getting a cup of coffee in here. So, again, this is like not even anything to do with the project, but this is just saying, hey, if we could do this, it would be really nice. Now, there is a tar file function, but I don't know how to undo the gzip. I don't know if we even have tar file on here. So what I can do is just go to a command prompt, and I, of course, need to execute some. Go to the right directory here, and then I can just run this is sat.py. Probably this is doing some other work right now, and so what I have to call is get satlib. And I can share this. So, wow, I got a 0 byte file. Interesting enough. So the first question, of course, is how do we get the file? I mean, that doesn't fly here. Maybe I'm just going to check that link is valid. Yeah, it is. It's downloading it again. It's 300K. So there is a tar file library. Oh, and it handles, okay, so actually this is easy. And it comes with Python. I mean, that's too easy. So probably we should make a variable for the name of this. Again, that's kind of like next stage though. So we call extract all and tar.close. Again, probably we want to like make a folder somewhere for this. This seems pretty sloppy. Oh, I think the problem is I forgot to put this stream equals true. I'm not sure right now. Wow. Whoa, it worked? No way. That really mucked my directory up though. So I'm going to unmuck the directory. And the way I'm going to do that is by just making another directory. So that's going to be my output directory, and out file equals os path join. Like, you know, starting to get this to a better place. Now, the question with tar extract all is, can we do something nicer with that? Like, how do we change the directory? Path. All right, let's try that all again. It's taking some time. It's doing something. Wow, works. Okay, that's beautiful. So now it's not at least cluttering the source code directory. It's control flow graph directory. As it's not the right place, but you know, it can be like it's more of like a scratch directory. And okay, so it works. I mean, the question is, how do we get these SAT instances, and how do we even read them, right? So if I open one of these, oh, okay, so I guess 01's the first one. Just open the first one. So there it is. Now we see it's a bunch of numbers, and they end with zeros, and it's got some comments in here. So the way we want to do this is first now, get rand3cnf. So now we want to return an enumerator. We're not actually going to return a, so we're going to start enumerating, and we're just going to pre-parse the clauses. We're just going to do the full job here. So no reason to delay the work. You got this, we already untarred, unzipped. I mean, that's pretty impressive. We already have it downloading from the web, untarring, unzipping, only doing it if it needs to. Now the untarring we should probably fix as well. Because I don't want any of this to be going on. I don't even want it to import requests or tar file. I don't want to do anything. I mean, if it's downloaded it, it's obviously extracted it. I want nothing to happen here, just like an OS path exists. That's enough work. So now what we have to do is we have to list all the files in the directory and find out what's going on by a wildcard. I forgot how to do this. Glob, yeah. So we import glob, and then we say glob.glob. Somewhere we want our usual out directory, just so we can change it later, generalize that however we want. And then we can just say outdir star.cnf. But let's be a little more specific. So we saw the file names here are all UF20 dash. So actually, just make it so we can manage this better. We may even make something to delete them and everything, and we can use these wildcards as long as we're sure nothing else will conflict. I mean, which we can be, because it's not very likely we're going to reuse that prefix for anything else. Then we could actually delete. We could make a management system. I see this is UF20-91, but whatever. So now glob is going to return. There's other ways of doing this, by the way. We don't have to use glob, but I think it's portable. I don't know what it's going to return, so I'm just going to, Oh, it's a list of path names. Okay. I still want to see it happen. So get satlib should probably have like a whole bunch of them that it gets. Uh-oh. Now it should do no work because it's already downloaded the file. Yeah, okay. Okay, so wow, we see all of the paths here. Okay, it's perfect. So now we can actually start opening them. And we can just say with open, file, read. Now we're going to yield a list of, or I don't know, a list of tuples. Okay, I mean, that's fine. We can make these whatever we want. Actually, tuples, almost a list of lists here, because we're going to do it kind of generically. So then we can actually print this from main and just make sure that it's returning SAT equations. So what we have to do now is we have to parse the file. So let's do that the most straightforward way possible. I guess there's a read lines function, so we could say for line in and this is the easiest thing to do. So now what we need to know is how to parse these files, which are in die match form. I think it's called die match format. For SAT solvers, yes, okay. There's an easy one. So if the first character is C for comment, we can continue, unless we want to parse comments, but right now we don't. Otherwise, all we want to do is split that string and convert them all to integers, and we're done. I mean, the zeros can just be filtered. We don't care. There could even be 2 zeros. We just don't care. Zeros are irrelevant. They do represent a terminator, but, maybe if we want to be totally efficient, we won't do it this way, but I'm forgetting how to do all these things in Python, but whatever. It's easy enough to figure it out. So we just say line split. Yeah, one idea is just to do it like this and just say, items. Instead of checking a character, we could just check that the first is a C. I mean, again, the only issue would be is like, what if it's an empty line? And probably we should handle that. So what we could do is say if length of items is 0 or the first item is a comment, we're going to continue. And then we can actually just like parse these things. and we parse the integer, I guess just using a cast, like a cast style thing, so we can just, well, somewhere we're going to want a clauses variable, so now it's going to be for each file, so we'd have clauses, is just a list here, and then we're going to have clause, it's going to equal to, you know, int of x for x in items. If x not equal to 0, I suppose, might be a nice way to go. In fact, we could just append it right here. Then what we can do is here we can just yield clauses. Just to test that it works. In fact, this should be enough to parse all of them. I don't know what's going on. Oh, because it's yielding. I'm being silly here. Okay, so we need to look at the file format again. I do see this percent and 0 lines here. P. So this actually tells us it's a conjunctive normal form, CNF, with 20 variables and 91 clauses. So we actually know how many clauses. Now I may want to just like look up DMUch format. Okay, yeah. But it's working kind of at least. I think we'll just continue on that condition as well. Oh, clauses can be split over multiple lines because of the 0. I'm kind of reading about on the DMUch page. I don't know what a percent sign is doing in there. I don't know what the percent is doing in there. I can't even find information about it. I'm just documenting this because, again, we may want to put the solution out in this same format because it's just such a nice kind of simple generic format. Oh, there's a little bit of trickiness to this, but I don't understand the percent or the zero after the percent. All right, so what we see is it's just always got these percents, and we can just break, I suppose, because it's going to have a zero after it. But otherwise, actually, these look good now. I look like I'm getting my SAT equations back. I mean, if we wanted, we could actually cast this to a tuple. It just doesn't matter that much. We can see how long it takes to parse them. Not a whole long time. So now we can actually start adapting this, and we've got SAT naive. I've also got other SAT solvers, like I got glucose and PyCryptoSat, PycoSat, all these different SAT solvers already installed in its Python packages. SAT naive, very simple. Oh, I see. It's going to keep solving it forever. Huh. But what I kind of care about here Okay, my check solution, and of course you want to have this. It's so, remember, these are problems that are hard to find a solution, but easy to verify. So you want to do the easy to verify part. Yeah, okay, here it is for XY in clauses. Okay. So this is really just a silly function right now. We should actually put this in C too. Okay, I'm gonna just call it check sol2 set. Because this is just so silly. It's too silly because honestly this is too easy to fix, but Something elegant about that simple code right there. So it found a solution. Obviously, it's only looking, at 20 variables, and that's why I did this. I didn't do hard ones, because if it's, 50 variables and 1,000 clauses, it's, possibly going to take length of the universe time to do something. With our naive formula, that just tries 2 to the n. Obviously, 2 to the 50, 2 to the 20, I mean, we can imagine we're going to get a solution. It's a lot of strongly connected components, but we'll get a solution. So let's see how things are going to go here. Okay. All right, so the next step is filling this in by not being naive about it, but by saying for clause in clauses. I'm just using a simple, well, any one of them has to be true. So we need to if any, or actually any has to be true, but the condition here really is if all of them aren't true, then we should return false. Again, it's the same code. It's just, as I said, that's why it's kind of silly to keep the 2-1 around. But again, we can just go for, for x in clause. Yeah, I want it to print something here. Yeah, I guess it will. Huh, that's interesting. So it's actually finding all solutions that quickly? That's crazy. 2 to the 20th. Well, I guess it's not that big. It's 2 to the 16th is, 65,536. So, yeah, 128,256,000. It's about a million strongly connected components. Pretty fast. All right. But guess where we are? DP. We can start now. I mean, we have our equations. We don't care that they're 3 sats, not sat, because again, it's the same thing. It's just actually a simpler testing. But we are already done with all the downloading, all this type of unzipping, all these details. We did it that fast. Yeah, the next one is 50 variables, 218 clauses. That, I believe, the SAT frameworks will solve, but of course, naive method, forget it. Anyways, let's do Davis-Putnam. That was fun. Honestly, that was fun. So this is DP. And what do we put here? We put the Wikipedia link, because that's what I'm looking at it right now, and, only fair. Put the comment up here. Okay, so it takes clauses, as usual. That's all you get. Okay, so what on earth does Davis-Putnam do? Checking the validity of first-order logic formula using our resolution-based decision procedure for propositional logic. I'm a bit perplexed reading this, but I see. I see in the picture on Wikipedia, it's like got a couple examples saying one if B is true, not B is not true. And then it's distributing. That's madness. Yeah, I kind of get it. It's not a complicated algorithm. It's doing, but it's like just randomly taking a variable and then, dealing with both its positive and negative cases, and then somehow like writing a new equation after that. Okay. So the first thing we're going to need is we're going to need a map from variables to clauses. So what we can do, before we kind of did something like get to-sat graph, now we're going to want a helper function, which is like a get sat map. Because we're going to use this everywhere, obviously, DPLL, CDCL. So this get sat map is going to take the clauses and just get the variables out. But while it's getting the variables out, like have some kind of map that maps variable to clause. So it needs a dictionary. Okay. Or we can find it like this. And so we can go for clause in clauses. Again, we're going to just assume sat, not 3sat right now. We're going to be very general, so this will work in any case. Again, this kind of like, it's not like we're going to be nearly as good as these libraries that have been highly performance tuned, but we're going to try to make this the most simple, elegant, demonstrative code of these algorithms so that we have a great model of the algorithm. Rather than going off into all the details of how to micro optimize them, we could even go to C++ and make it faster later, or use Python to do these options. But for now, for x in clause, if not x in map, map x equals again, we could like index the clauses, but actually in Python it should do things by reference. Yeah. Because we want like this to be like a set of all of the clauses. Because we could do like something like this, add clause. So we get the map. So now we have something that goes from the problem. Well, if these are references, this will be good because, we're going to get these problems as we try to resolve these. Who knows what's going to happen here? As far as I can tell, we can just choose a random variable in the map. I'm a little confused on how they want to do the resolvent part. I have to go look this up again somewhere else. I want to see a better description of this algorithm. I almost feel like I have a better description of DPLL. Yeah, one thing we could do is delete some clauses, possibly. Hmm. So what I'm seeing right now is that what we do is we go through each variable, and yeah, there's a little bit of this kind of sketchy. Feels like we have to go through each one. I basically get it here, but I'm still a little bit fuzzy on a couple things, so I'm going to try to work this out in my head. This is like the hard part right here. This is an old algorithm that nobody uses, but it's well worth doing the implementation of it because it gives you a whole historical context. So obviously we're going to choose an arbitrary variable, and what we want to do is we want to go through clauses and kind of apply that variable in a way, which means that if it's true, actually the whole clause becomes true and you could actually delete the clause. Although it seems like instead it leaves the what they're calling the resolvent, the remaining possible ones behind. But then the negations, you definitely just delete it as well. So I'm kind of like wondering how to do this resolution part. Add all resolvents over that variable. Then delete all clauses with that variable. I mean, they're talking about tautologies. Tautologies are easy. These are just having, x and not x in the same clause, which is impossible. The problem is this method will make it very hard to keep up with the enumeration of all solutions like we've been doing. That's going to be tricky. So resolvents. I don't understand this resolvent stuff. Okay, the resolution rule in propositional logic. Oh gosh. So we're not gonna have to do the negations. Oh yeah, that's the whole trick behind this. So the whole trick behind Davis Putnam is that what we do to get the resolvents is we're saying that B is either true or not true at the same time. Ah. Ah. Okay, okay. So first, so you do them at the same time. You sort of say, if it's true, then we basically know that two clauses are true, and we know in the other two clauses that it's not true. But then we do the opposite. We do then, oh, the other way is true. Hmm. So if P, I'm looking at an example here. If P is true, then we have Q or not, and we have another clause with not Q. Yeah. Q or not Q is always true. Yeah, that doesn't matter. How are they getting this resolvent? They're doing like a little bit of Boolean combination here, and that's what I'm missing right now when they say getting the resolvents on P. Because if you apply not P here, then that's true. That's true. And that becomes Q, and that becomes not Q. So I'm not seeing this. Mm-hmm. So one thing is we don't necessarily want I guess this doesn't actually give us a solution. It is kind of interesting to study a really old algorithm. So I think we make a set and we can just, this one I guess is just going to return sat or unsat. So still looking for a better example of this. Okay, Davis and Putnam. So we have to do several rules here. We need to do unit propagation, pure literal elimination, and case splitting. This is actually the best description I've seen of it. Obviously, the Wikipedia one is kind of not perfect for doing an implementation. So the first idea is that if there's any clause which remains with only a single variable in it. Now, the problem with this type of routine is, well, we'll need both the map and the clauses, but we can do this like unit prop takes like clauses and map, because this actually resolves probably one of the most important conceptually. Practically, and making this extremely fast is so important. It's probably the slowest part of SAT, but we're just going to assume that this is, sufficient for now. You can't get much more simple than the strategy we have here. So the idea is that we can, for clause in clauses, if length clause equals 1, then we know we have a unit clause, and so we can simplify all the other clauses. Now, the problem with this is that when you find one with length 1 and you simplify all the others, now, while you're simplifying the others, you may find more that have length 1. And so it's, you're going to have to think about what to do about that. But anyways, what we can do is, since we have a map now, we can actually use that map to simplify all the other clauses. So we can say for C in map sub. This clause we can actually delete. Yeah, actually, this is kind of tricky to write perfectly, but that's what we have to do. There's no choice. We can go through this right now. And excuse me for a moment. So we're going to actually go through map of clause sub-0. And yeah, sorry I'm thinking so much, but again, that's what you have to do. You have to go look at some papers, go look at some articles, go look at Wikipedia, go look here, go look there, and look at a variety of sources until you find something that puts it in terms that, oh, I'm ready to code this. Because I know this isn't that hard, but I also know you do need to think about it, especially the data structures, but also, you know, where they're doing some propositional logic and you don't know the notation or the terms they're using. So, basically, we can actually just start going through these clauses and start, you know. Oh man, so actually, one problem we're going to get here is that if we go through the clauses and try to change them, well, if they're tuples, that's a big problem. So I mean, again, that's not efficient at all. So we're probably not going to use tuples in that case. What we'll want to use are sets. I mean, I guess we can use it for now. It doesn't really matter, but this actually, it does get into a number of issues because we need to be able to delete the clauses as well. Otherwise, we'll have empty clauses. I guess we don't have to, but it's not efficient to have empty clauses. But then we have to use like a set of sets, which you can't do. Maybe a set of frozen sets, but then we have to modify the frozen sets. So whatever we do currently, I'm seeing some inefficiency here. Yeah. A set of sets seems kind of reasonable, though. Okay. Let's just make a variable. So the negation is just going to delete from the map. So we can go through both of these. We can go for C and map some negative x. So the first thing we're going to want to do is get all the clauses. So we're going to have to pre-do this because we're going to modify clauses, I suppose. So, although as I point out, if it's not a set, again, there's lots of data structures. Some people are using trees and other stuff, and we may want to think about that. So we basically want to do this operation. I don't know what name to use for different things. Actually, we can just use C everywhere. It's a different C. Ultimately, it doesn't matter. Anyways, okay, let's call this clause. That's fine. Actually, that's fine. Because we'll use C again here. So now we're going to go through the clauses. Then the true clauses, it's already true, so we don't need that anymore. So in the true case, you actually can just delete it, the clause altogether. But if we delete it, the problem is it'll still be in the map. So first we want to delete it from the map. The other problem is this will be irreversible if we do this. I'm seeing lots of data structure problems coming up right now, just a whole slew of them. So that's what we do. We delete the satisfied clauses, and we remove minus x from the other clauses. In the end, though, we're going to actually say map.remove x and map.remove minus x, because technically these are resolved now after you've propagated it. Okay, I think we're ready to go through the maps and do this. I'm just trying to think about data structures here because I haven't, I'm not taking like a framework and just, I'm doing this from scratch. So I have to really think like, we can put in elegant data structures later, but right now we want to do something straightforward. So for C in map minus x, we actually want to just remove. Now, doing a list remove isn't ideal, but I guess for now we can think about that in the future. We also could just delete everything. We could just... Problem is, deleting everything is basically what we are doing, but... Problem is we have to clean up the map as well. Ooh, this is, yeah. So we go through all of the references to this clause, and we just delete the clause because, obviously the clause doesn't exist anymore. It's already been satisfied. Then we remove the clause. Now, in that case, then we don't need to remove this here. Well, that seems pretty tricky. Now, about the tautologies, that's like another aspect where you have x and minus x in the same clause. Okay, so we go through the ones containing it, and we can just delete them. It's true. So the whole clause can be removed. It's already been satisfied. It won't help us make any more deductions at that point. So we go for Y and C, we remove all of those, and then we delete the clause itself. I think that's okay. And then we do the minus x and we just remove that variable, the false case. Now, could we end up with an empty clause here? Yeah, we could. So we can clean that up like this. I think, again, this isn't efficient. This is definitely removing from lists and stuff. This is not going to be anything we want to call efficient at all. We have to rethink the data structures. Really, really rethink them. And we can just, actually we can still leave it as a list of tuples. We can always just convert it to whatever ideal data structure at the start. That's usually what you do. I mean, that's, the order of that is relatively straightforward. It's obviously order of number of clauses, or order of clauses times, the average size of the clause. But whatever, I mean, this is not a big deal to do a conversion like that. So now pure literals. So we do the pure literal elimination, which means basically there is, now we go through the map. So what we can do is we can say for var in, we'll say m for m in map, if the length of map sub m, if the number of clauses for this particular map entry is 0, so like if not something or not something is not in there at all, then we know that the opposite must be true. Now, what happens if like a variable is not referenced at all? Well, it wouldn't be in the map in the first place. So either true or false has to be in the map, and it has to at least have one clause. So at least right now, I'm not anticipating a problem with this. So now, again, we've done this so we can update the map. So we make kind of a copy of this list first, just checking all the cases. Now, as I said, this particular case could cause more propagations here. And this is where you would like, if length C equals 1, now we actually want to like add it to some list, you know, I'm going to comment that now, but obviously this isn't the end of unit propagation because we have to keep doing this until these next clauses no longer exist also, because this one unit propagation could cause another unit propagation. In fact, it could cause the whole SAT system to solve. Now, we may want to record what was solved as well. So that's another thing. I would say if we return something, solved vars, and so now we can actually save all the solved variables because we might not just want sat or unsat. Now, I don't know with this DP method if we're going to be able to easily do this, but in the future we're going to want this anyways. So this function's very, very important. It's like at the core. The tautologies, though, is something else to think about. Yeah, because like if X and not X are in the same clause, obviously I don't see that tautology being mentioned anywhere here. The easiest way to do this is to just use the map for that, I believe. So anyways, we've found a variable that's not referenced. Then we know that minus var must be referenced. So the idea is we're going to let these different rules work together. So the first thing to realize here is that we should just add a unit clause so we can allow the unit propagation to do its job. So we can just do like this. And this isn't going to resolve the variable. It'll be resolved here in unit prop. It'll just say, okay, the variable's never referenced, so its negation must be referenced somewhere. And yeah, as far as I see, this is all we have to do here. That's the pure literal. It seems very simple, right? And actually, this is efficient. What's not efficient is removing them. But appending to the end, I mean, there's nothing too wrong with that. We just need a faster way to remove these clauses. Okay, so that's the pure literal. Then finally, we have the case splitting. Yeah, it feels almost like for what I'm seeing, the DPLL almost looks easier to implement here. We're going to call this DP and we'll just change the comment. So the first thing again here is getting the map. Because actually what I was starting to write here is actually supposed to be a different rule. But the problem is, the idea is this case splitting rule is a problem because it requires F to be put into a different form. And so we're going to have to look at how to do it because we need to put it into like more of a disjunctive. No, wait. This is conjunctive. Oh, no. I see. Well, okay. But anyways, we're going to have to take some random variable and just apply some simple rule on it. It's very simple. Yeah. Actually, maybe we should do, yeah, maybe I'm getting ahead of myself with the DPLL. This doesn't look that bad. The case splitting algorithm is applying this logic here. So we can actually say that so if minus var never occurs, add that clause. Okay, so minus var never occurs, then we add the clause. This one is saying if a clause equals var, only var, because that's like a set with one element, remove all clauses containing var, and containing it. It's kind of a little confusing, but yeah, you remove all clauses containing var because they're already true, and you can true clauses you can just remove. And then the minus var, though, you can't remove the whole clause, but you can remove minus var from the clause. And so that's, okay, that deals with that. Now the case splitting is going to apply a different rule. It's going to say A and okay, well, we can say A and var. Let's just use P and Q. P and var, or Q and minus var. And this is kind of a logical, Boolean logical replacement, a deduction here. It's going to equal to P. Wait, what am I saying here? That was disjunctive normal. Obviously, I want to say the opposite of this. So basically, here's the problem, is there's going to be a lot of these. Now, I don't see where it's dealing with the tautologies here. Because if you get A or not A, it's always true. And so I don't know. I mean, it feels like those are basically useless clauses. I'm thinking we should have like a tautology, because the problem is we could do it here because the only place we're adding clauses, but what if it already had a tautology? We want to get rid of it anyways, so we are going to complete these last pieces of code. This one's actually not too bad if you think about it. So the idea is we could take any var out of the map at this point. I would actually say let's actually allow it to choose the variable. Now we don't care if it's var or minus var, it's going to be exactly the same thing here. But what we have to do is potentially have an exponential number of cases here. That's the disadvantage, and this will break it from 3-sat actually into a broader sat problem. But it should still be reasonably efficient here, I imagine. The problem is the value of this variable won't get assigned. So if we get like a partial solution, I'm not exactly sure how we would fill this in, because we've essentially, logically eliminated this by increasing the number of the size of the clauses and the number of the clauses. So anyways, if we have the var, we can just, for m in map sub var. Well, here's the key. We're going to need to go through not only map sub var. Now that we can do, we could even say for like n, or let's even just use the p and q. For q in map sub minus var. Again, we're now just doing some basic logic, and now we just combine the clauses together without var and minus var in them. But the problem is the tautologies obviously would have to be resolved, or we would just get some ridiculous blow-up. So I don't know, but we're going to have to do that. There can't be any tautologies before, at the beginning. We can do it once at the very beginning, and then after every case splitting, we would also need to do it. So the easiest way to deal with this might even be, yeah, it's kind of like an initial construction. It might even be before we do this get sat map. It's just, this is such a silly thing. We're just gonna, we don't need the map if we don't have it yet. I mean, we have to think about that. But I would say, let's do this one just on clauses. So, it might be easier to do with the map. So we go through all the variables. Actually, here is where we don't need to go through all of them, because we don't have, if we've done the negation, we don't need to do things twice. That would be inefficient. So there's other ways we can deal with that, of course. Okay, so if C is in maps, for C in map M, so we go through all the clauses and we say if C in maps sub minus M, then we can just remove the clause. Problem is we have to update the map. Can we update the map? Well, we can if we're doing it like this, but if we, made like a set. So we can actually use a trick here where we just say, okay, first off, we're making a copy of all the keys in the map so that we can actually change the map. Okay, can we do this? No, because we can't update this one either, huh? Okay, so we make another, again, always the solution we're going to use right now. we make another list, so we're no longer enumerating map sub m. And okay, we can actually do it like this now. Here, yeah, here we have to do it so we can update map. Oh, actually, do we need this? Oh. For now, it doesn't matter. We can actually probably don't need it here, but here we do. So it's very similar to what we did before. So for y in C, map sub y dot remove C type of stuff needs to go on. And of course, y will also be m at one of the cases, and it'll be minus m. It'll be, of course, it'll have, we're just getting rid of these clauses because they're certainly, if it's true or not true is always true. So, you know, it's a tautology, it can be removed. So we can actually kind of remove this one. What we want to do is take like a random, I'm just going to use next iter to get it, and then I'll just say case splitting clauses map. Of course, we're going to need to call these other functions like unit prop clauses map and pure literal clauses map. I kind of think pure literal should be done first. I don't understand why that would be done second. So, of course, the problem is these two are going to have lots of effects on each other. We almost want to know some information, like, again, returning some information about when this is happening. We could even say it's a solved var, even though we haven't applied this rule, which will solve it again. We could actually, you know, do something like that. This way we can actually enumerate and do these resolutions before we do the case splitting, because the case splitting should obviously come later. This is the worst rule in the DP algorithm, and the reason DPLL was created to not do this anymore. So what we have to do is do this, you know, exponential combination now, and then we can actually delete them from the map, and we can delete all of their clauses as well. All of their clauses are going to be gone because we've created new clauses to take their place. This is kind of nasty because we've got to update the map a bunch. It's not just this, but not only are we deleting all those old clauses, but when we're adding these clauses, we have to add them to the map. I guess it's, again, I'm making a big deal out of this. It's not that big a deal. It's just, computationally, it seems kind of ridiculous. But, and the problem with the whole DP algorithm is this step seems to be causing problems. This step is meaningless in a certain regard. So, yeah, I kind of feel like something like this does the job. Again, the tautology can only appear at the start or after a case splitting. These can't cause a tautology because they're just reductions. But after this, we need to call tautology again. But actually, if we did this in like some kind of while loop, like as we're kind of slowly structuring this too, we could always just do tautology first after the case, you know, the random case splitting, which just use a random variable. We don't need any of this resolve stuff. And then we somehow have to decide at the end if it's sat or unsat. So if this becomes an empty clause, I forgot how we're doing this right now. I guess we're returning, we're enumerating solutions, this is at least the theory, but so we can do something like unsat. This is the unsat case. If it gets to an empty amount of clauses, if it doesn't get to an empty amount of clauses, then it has like some kind of partial solution left, and yeah. Let's see. This part is the main part that I haven't really coded anything for yet. Plus, these two steps need to be applied before case splitting, as long as there's more eliminations to do. And probably we want to start recording a solution to see the problem. This case splitting, it really is. I have to think about how we're going to recover the value of, should it be true or not true for the value that it's chosen for this variable. I think we'll be able to figure this out. I think there might be a trick for that, because it would be cool to have this old algorithm really implemented properly. So if we go through the clauses in map var, we can just remove, well then we go for y in C, and then we can actually say yeah. I think we need to do the same thing again. Of course, then these will be empty anyways, because we've gone through all their clauses, and ultimately we've removed them all. We'll need something like this. Just because we can't modify a map for this one because we're enumerating it. But we're going to take care of it down here. So we remove it, or remove all the clauses. And did we remove the clauses themselves? No, we didn't. Now building the new clauses. Well, building the new clauses is easy. It's just P or Q. And what's P or Q? Well, it's this without the, it's this one without var and this one without minus var. Yeah, I feel like we could detect the tautologies right here as well. We don't want, I mean, again, we just think about this as time goes on. So now, this is a tuple. We know we're not going to get away with something like generator number 1. Generator number 2. So here's 2 generators. What we can do is make a big tuple out of them. I don't know if this is really an efficient thing to do like this in Python. Use the star operator here. And then this will give us the new tuple that we want to add. So we actually just say clause equals this, and then we can just say clauses.append clause. So now we have a new clause. However, as we know, we're going to need, now we don't need to like worry about this case that we did up here, but we do need to add all the variables. So, for x in clause map sub x dot add pen, maybe it was, I don't remember, add. It's set. So now a bunch of this is probably not going to work yet. This is fun though. This is actually, it's kind of fun. Wow. Yeah. Actually, that's a kind of a lot of code for this. I mean, yeah. Kind of a lot of code we have to write. And again, we're not even really efficient yet. I mean, hash tables and stuff are nice, but again, we've got lists here, we've got tuples, we've got a mess. It's going to crash. I'm sure I didn't get it right, but I kind of just want to play around with it for right now. It's the whole point here. We take out the sat naive now, and we actually start calling DP. And of course, we know it's going to crash immediately, but we want to see it do that anyways, just for fun. Oh, look at this. It's still solving. Wow. All right, so if I can get my syntax right, why things might be okay. Write a bunch of code. Start debugging it. Messed up all my... Oh, tuple expected at most one argument got 4. I guess we don't need to call tuple then. We could just use the parentheses. Oh, yeah, we can't, that's true, we can't do that. So tautologies just give us elimination with no information. Basically clauses that aren't even helpful. Solved, this one, pure literal, gives us solutions, but we're going to get those solutions again at unit props. So one thing to do is just to actually put it here. Okay, yeah, it is questionable to do it this way. So there we go now. Now it's going to do this in a loop, making sure it does the easy eliminations before it does this really tricky case splitting. Oh, so it's trying to remove clauses it just added, but yeah, that makes sense. We might want to save those around, but why on earth would this happen anyways? I mean, I admit it's totally useless code like this, but we can restructure it pretty easily. But why? I don't see it. I just don't see it right now. Because I see we're adding it. Accent clause. This is the new clause we're adding. Well, let's print out the clauses we're adding. Wow. See, this is what a chaos here. That's a lot of clauses. Again, they're bigger clauses than we used to have. So this was added in the first iteration. I think. Looks like it. Oh, actually, no. These shouldn't have any effect. No. There's no problem with all this. Oh, I see. Minus 16 is occurring twice in here. Ooh, that's why it's happening. One idea for this then is to actually, if we're expecting it to be like that, we can just use a set union. And then we'll just call tuple again. Well, I mean, honestly, this isn't that bad. You have to say that actually shows that we're getting somewhere now. Again, I don't know what's going to happen here, but uh-oh. What is it doing? Oh, I see. It's printing those. Probably my system's going to just run out of memory. May want simpler, I want even simpler stat equations. Nah, I mean, actually not really. I can't even find Python, it's using so little memory. It's using CPU, I think. Yeah. Oh, it's not using any memory for this at all. It's almost like it's just stuck. I want to see if it's actually solving any variables. Oh. Yeah, you can see the exponential equation blow up here. The map's getting smaller. Okay, these are already really small instances, but I'm definitely looking for like a even simpler problem here. Because the first thing you want to do is just confirm that your algorithm is right. Uh, obviously it runs now, but this isn't anything that I want to be seeing. I mean, yeah, okay. So it is eliminating two variables, but we see the number of uh, clauses that it's adding is just absolutely ridiculous. And it's never finding even one literal in the mix here. I just can't tell if it's working right now or not. Taking a look at some other, they're getting worse. I'm not finding any that are simpler. I almost want to write a generator at this point. Hmm. I know. I want some really simple cases because I don't know if the unit propagation and this type of code is working at all yet. Hmm. Well, if I search for SAT problems, I get the SAT. That's not what I want here. So now I'm looking for a good simple example. The perfect simple example. You know, a few variables and a few clauses. I could write one by hand. It's not that hard. All right. Here's one. Here's one that I found on the web. Let's just cancel this, and we'll try this test formula. One, two, three, minus one, minus two, three, and 1 minus 2 minus 3, and one more clause. So 3 variables, 4 clauses. This is, again, just calibration here. do that right. Okay. Unit prop. Now, at least we're finally, you know, getting a clue here. So I think what's happening is we can get a clause that's already been deleted. Wow. -2, -3, 2, 3. What? I mean, it looks wrong. It looks like it's giving some kind of unsat, because -2, -3, 2, 3 is a perfect example of like, it's going to eliminate those. I guess yeah, it should kind of eliminate those though. The true ones eliminate them. Yeah, the negative ones eliminate it. It will eliminate everything. Of course, if it does that, I don't know why I'm not deleting maps of X here. Yeah, I mean, whoa. Okay, maybe this will work. Yeah. But this is a wrong answer. I mean, this looks like what happens when it's unsat. But the formula I put 1, 2, and 3 all being true should satisfy the formula. So one thing we want to do then is just kind of look quickly. Because I have a feeling we're about to get this one solved. But so we'll just print map clauses. Okay, we see 2 minus 3 minus 2. 2, 3 minus 2. We see the different clauses. So what's happened is it's eliminated 1. So when it eliminates 1, it'll see 2 and 3 with not 2 and 3, which is useless. It's a tautology. So that's right. And it'll see 2 and 3 with not 2, not 3, also a useless tautology. Oh wait, 2, 3 with 2 and not 3. Yeah, that's right. Okay. I don't see this right now, but it definitely, from the logic I see here, it really shouldn't work. I mean, all the combinations will be tautologies. Hmm. I have to think about this because this is such a basic case. That's why it's perfect. Okay, I think actually I'm going to continue because I want to do some things before I continue this, but I'm going to continue this. This is a fun problem, and we're going to make real traction on it. Honestly, the traction we've made so far isn't bad, but really needs to be thought about. Again, I've never done this algorithm before. This is an old one. Nobody does it anymore, but it is really instructive to start this way. I mean, you can see. Uh, Again, it's just going to give you the really deep, proper understanding, especially if we could generate all solutions using this, or even a solution. I mean, again, it just shows your depth of understanding if you can do it. I mean, with DPLL, we're going to get solutions. This is a different type of an algorithm, and there's lots of variants of it and what have you. And then we'll go to CDCL, and we'll do it really the elegant, modern algorithm. And we'll see if we can do something more efficient in Python to, you know, use some kind of hash tables or some kind of clever trick to make it reasonably performant. We won't like make it totally optimal. There's going to be some data structure issues, I think, without going to some more specialized data structures. And that's honestly what most people are doing with the top SAT solvers out there. They're just coming up with clever coding and data structure tricks to make it really fast. So, okay, we're going to continue this later though. So, okay. So for now, I'm going to sign out, and that's it.